Welcome to the Trane Engineers Newsletter Live program. Now, there are many types of HVAC systems, and one way to classify them is into centralized or distributed systems. An example of a centralized system is a multiple zone VAV, while common distributed systems might be fan coils, water source heat pumps, or VRF. Now, both centralized and distributed systems each have their advantages and drawbacks. For example, over the years, one of the significant energy-related benefits of a centralized air system has been airside economizing. But in some cases, economizers have not lived up to the expected energy savings. So, the goal of today's program is to understand how to achieve the desired energy-saving performance from an airside economizer. To start out, we'll briefly discuss what an airside economizer is, review current and upcoming code requirements, and talk a little bit about expected energy savings. Then we'll review several of the common problems that occur related to economizers and how to prevent or minimize those problems. Trane application engineers John Murphy and Eric Sturm will be walking us through the discussion today. So John, can you refresh our memories about airside economizers?
Just to make sure we're all on the same page, ASHRAE 9.1 provides the definition of an airside economizer. It's a duct and damper arrangement along with automatic controls that allow the system to supply outdoor air to reduce or eliminate the need for mechanical cooling energy during mild or cold weather. Here's an economizer implemented in an example package rooftop unit. For much of the year, the unit brings in just the minimum amount of outdoor air required by the building code. It mixes this with recirculated return air and then cools or heats this mixture as needed. But when it's sufficiently cool outside, this outdoor air damper opens further to bring in more outdoor air, reducing the need to operate the compressors to provide cooling. Automatic controls are then used to decide when it's beneficial to bring in this additional amount of outdoor air. I'll briefly demonstrate this control using the psychrometric chart. When it's cold outside, and the system has provided heating air to the building, you likely don't want to bring in any more outdoor air than necessary. So the outdoor air damper is at the minimum position required for ventilation. But as it warms up and the system is asked to cool the air being supplied to the building, the economizer control modulates the position of this outdoor air damper further open, using this cool outdoor air to provide all the cooling needed. This is called the modulated economizer mode, since the outdoor air damper is allowed to modulate beyond its minimum position to provide all the cooling needed, and the compressors can be turned off. Now, when the dry bulb temperature of the outdoor air rises above the current supply air temperature, the system will need more cooling than the outdoor air alone can provide. Here, the outdoor air damper remains wide open while the compressors are activated to provide the balance of the cooling needed. This is called the integrated economizer mode, since the economizer and compressors are used in combination. Then as the outdoor temperature continues to rise, it eventually provides no cooling benefit. At this point, the outdoor air damper closes back down to minimum position, and the compressors provide all the cooling needed. Now, this decision to disable economizer operation is typically made automatically by comparing the condition of the outdoor air to a set point called the high limit shutoff set point. Now, there are various shutoff strategies that have been used over the years, so I'll just mention a few. And then Eric will talk about what's required by current energy standards. This first one is a fixed dry bulb control strategy, which I showed in my previous chart. A sensor is used to measure the dry bulb temperature of the outdoor air. The controller then compares this temperature to a predetermined high limit shutoff set point. And the economizer is disabled whenever the outdoor temperature is above this limit. Now, the best choice for this set point really varies based on climate. For more humid climates, a lower set point is often desired to avoid bringing in too much humid outdoor air, while for drier climates, a higher set point results in more energy savings. Now, differential dry bulb control uses sensors to measure the dry bulb temperature of both the outdoor air and the return air. The controller then disables the economizer whenever the outdoor temperature is warmer than the return air. That is, it uses the cooler of the two air streams. Next is fixed enthalpy control. This strategy uses sensors to measure both the dry bulb temperature and humidity of the outdoor air. The controller then calculates the enthalpy of the outdoor air and compares it to a predetermined high-limit shutoff set point. The economizer is disabled whenever the outdoor enthalpy is above this limit. And finally, differential enthalpy control uses sensors to measure both the temperature and humidity of both the outdoor and return air. The controller calculates the enthalpy of both air streams, and the economizer is disabled whenever the outdoor enthalpy is higher than the return air enthalpy. That is, it uses the airstream with the lowest enthalpy. Now, the best choice for high-limit shutoff control really depends on climate, building use, and utility costs. So we'll talk more about this in a little bit. Eric?
That's a good overview, John. Airside economizers are mentioned in several standards and codes used within the building industry. Examples include ASHRAE Standard 90.1 and the International Energy Conservation Code from the International Code Council. Some jurisdictions have local codes. In this broadcast, we're going to focus on Standard 90.1 and the IECC. In the past few years, there have been some significant changes to both, so let's take a few minutes to explore those. First, we'll start with Standard 90.1, and I'm going to talk about several versions of 90.1 because usage is fragmented. There are a number of states with energy codes that use the 2007, 2010, or the 2013 version. In the past, economizers were prescriptively required for cooling systems with fans of varying sizes in different climate zones. The standard says air economizers must be designed to provide up to 100% of the design supply air quantity as outer air for cooling. The standard also requires the economizer dampers be capable of being sequenced with the mechanical cooling equipment, the integrated mode John talked about earlier. There are certain climates where economizer usage makes sense. This map comes from the 2007 version of 90.1 and shows where economizers are required given system sizes. Systems greater than or equal to 11.3 tons are required to have an economizer when installed in cool and moist climates. These climate zones are shown on the map in blue. Systems in warmer and drier climates, shown on the map in red, require economizers when the system capacity is greater than 5.4 tons. The southeastern United States, shown in gray, does not have an economizer requirement. The 2010 revision to Standard 90.1 significantly expanded the geographic requirement for economizers. This update also reduced the cooling capacity threshold from 11.3 or 5.4 tons down to 4.5 tons. So economizers are now required in more climates and on smaller systems. As you can see here, nearly all climate zones require economizer usage when the design cooling capacity is greater than 4.5 tons. Notice the very southern tip of Florida, climate zone 1A. Here, economizers are not required. And the map for 2013 looks just the same as the 2010 version. There are several requirements for economizer usage in systems that serve computer rooms, but we're not going to focus on that today. Those requirements are included in your handouts. The standard also includes climate zone dependent requirements for shutting economizers off, the high limit shutoff John talked about earlier. There are specific high limit shutoff set points for different economizer control types and climate zones. Here's the table of economizer control types and high limit shutoff set points from the 2007 version of 90.1. It lists the various control types, which climate zones each control type is allowed in, and the required high limit shutoff set point. You can see that there's a wide range of permitted controls available to designers. For example, consider a package rooftop being installed in Danbury, Connecticut. This is in climate zone 5A. If the unit is controlled by dry bulb temperature, the set point will be 70 degrees. And if it uses fixed enthalpy control, it'll operate when the outdoor enthalpy is less than 28 BTUs per pound. The 2010 version removed the fixed dry bulb temperature control for all other climate zones, but the rest of the table, like the song, remains the same. There are a number of other changes to the economizer control table in the 2013 update. First, the fixed dry bulb control was expanded with a third set point condition for hot and humid climates. Second, the electronic enthalpy control was removed as an acceptable control option. Next, two new control types were added: fixed enthalpy with fixed dry bulb control and differential enthalpy with fixed dry bulb control. These two new controls are similar to the previous fixed and differential enthalpy controls, but with a new dry bulb component that ends economizer operation if the outdoor air dry bulb temperature surpasses 75 degrees. John, what do these controls look like on a psychrometric chart?
This first one is similar to fixed enthalpy control. But like Eric mentioned, it adds a fixed dry bulb limit too. That is, the economizer is disabled whenever the outdoor enthalpy is above 28 BTUs per pound set point, or if the outdoor dry bulb temperature is above 75 degrees. Now, the motive for this change is that if the conventional fixed enthalpy control is used in a dry climate, the economizer will bring in 100% outdoor air when it's hot and dry outside and may actually increase cooling energy, even if the outdoor enthalpy is lower than 28 BTUs per pound. Here's an example of one of these hot, dry days. The enthalpy of the outdoor air is below the shutoff set point for conventional enthalpy economizer control. So the economizer opens the outdoor damper to 100%, and the coil then cools this air to the desired supply air condition. However, with fixed enthalpy plus fixed dry bulb control, the economizer would be disabled at this condition because the outdoor dry bulb is above 75 degrees. So return air mixes with the minimum outdoor air, and then this mixed air passes through the cooling coil. But look at the difference in load on the coil. When the economizer is disabled, the enthalpy difference across the cooling coil is less than if the economizer were to be enabled. Now, because of the dry outdoor conditions, the cooling coil isn't dehumidifying. It's only removing sensible heat. So if the outdoor air is warmer than the return air, it might take more cooling tons to get the same supply air temperature. So the standard 90.1 committee added this dry bulb limit to fixed enthalpy economizer control to prevent this issue. In the same way, the fixed dry bulb limit was also added to differential enthalpy control as well. In this case, the economizer is disabled whenever the outdoor enthalpy is greater than the return air enthalpy, or if the outdoor dry bulb is warmer than 75 degrees.
Another new change in the 2013 version deals with sensor accuracy. Specifically, the standard now requires outdoor, return, mixed, and supply air sensors to be calibrated. For dry bulb and wet bulb sensors, the accuracy must be within plus or minus 2 degrees over the range of 40 to 80 degrees Fahrenheit. For enthalpy sensors, or sensors that compute a differential enthalpy, the accuracy must be within plus or minus 3 BTUs per pound over the range of 20 to 36 BTUs per pound. And finally, for sensors measuring relative humidity, the accuracy must be within plus or minus 5% over the range of 20 to 80% RH. These tolerances seem pretty reasonable, and it shouldn't be terribly difficult to find a sensor that meets the relevant requirement. There are a number of exceptions to exempt economizer usage. The 2013 version of 90.1 lists 10 exceptions, with some having multiple components. Some exceptions are specific to building or space types, such as hospitals and ambulatory surgery centers, supermarkets, and computer rooms. Other exceptions exempt economizers if condenser heat recovery is used, or if cooling equipment efficiency is increased by a climate zone specific threshold. Last year, we published an engineer's newsletter on economizers, and in it, I paraphrased the exceptions that apply to systems that serve comfort cooling applications. You can find a link to this newsletter online and in your bibliography. Next, let's take a look at the economizer requirements in the International Energy Conservation Code. This is a model code that jurisdictions, such as cities or states, may adopt or may modify and adopt. Like 90.1, it's published on a regular schedule, and adoption is somewhat fragmented. There are 3 paths to comply with the model code's commercial energy requirements in Chapter 4. One path is to follow Standard 90.1, while the other 2 paths include meeting a series of requirements with the possibility of making an energy model. Economizer usage is included in both paths. These requirements, in general, are very similar to those published by ASHRAE in Standard 90.1, with some differences, such as different capacity requirements, Economizer Exceptions, and the addition of Economizer, fault detection, and Diagnostics. The code requires air-cooled unitary direct expansion units, such as package rooftops, water source heat pumps, PTACs, and VRF units, to include a fault detection and diagnostic system when an economizer is present. We're going to talk about fault detection later in the broadcast.
Codes and standards require economizers because they save energy. How much they save depends on climate, operating hours, loads, and so on. So Eric, how many hours can economizers be used?
That's a good question, Jeannie. One could evaluate a weather file to determine when the out-air dry bulb temperature is less than a high-limit shutoff, or one could evaluate when the out-air enthalpy is less than 28 BTUs per pound. We did just that for several cities in different climate zones around the United States. For this analysis, we needed to determine operational hours, when the building would be occupied and when the system operates. So we assumed an office building that is operational on weekdays from 7 a.m. to 7 p.m. These assumptions yielded 3,024 operational hours per year, or about a third of the year. Based upon that, we were able to determine which hours an Airside Economizer could be used. So here are the cities, starting in Climate Zone 1A with Miami and moving north: New Orleans, Atlanta, St. Louis, Boston, Minneapolis, and Fargo. In the drier portion of the United States, we have Tucson in Climate Zone 2B, and again moving north, Las Vegas, Albuquerque, Boise, and Helena. Finally, on the west coast, in the marine climates, we have San Francisco in Climate Zone 3C and Seattle in 4C. So let's start by looking at the moist climates. This chart shows the location, climate zone, and number of hours where an economizer could be used with different control types. 3 controls are shown: fixed dry bulb temperature control, fixed enthalpy control, and fixed enthalpy with fixed dry bulb. This last one is just like the new control in Standard 90.1 that we described earlier. These are the climates in the eastern and central United States. As expected, of the 3,024 operational hours, the least amount of economizing would occur in the hot and humid climates where Miami and New Orleans are located. But even in Atlanta, where it's still hot and humid, there's a significant number of hours where the out-air dry bulb temperature is less than the high-limit shutoff of 65 degrees. If the economizer control is based upon the out-air dry bulb temperature and enthalpy, there are some significant opportunities for economizing, just over a quarter of the operational hours. Moving westward to the dry climates shows even more potential for airside economizing. The 2 marine climates are shown in the rightmost side with a lot of economizing hours. In most of the climate zones, there is a potential for a lot of hours where the occupied spaces can be cooled with partial or no compressor usage. We've done some energy modeling to show the benefits of economizing as well. John, what did Trace 700 tell us about economizing?
We performed a trace analysis for 2 example buildings, a retail store and an office building. Both were located in Columbus, Ohio. The purpose was to compare the energy savings of various economizer control strategies and set points. The first study was for a constant volume rooftop unit serving a retail store. Now the y-axis on this chart shows the annual HVAC energy use as a percentage of the baseline system which does not have an economizer. So for this example, the Airside Economizer reduced the HVAC energy use by 8 to 16%, depending on the high-limit shutoff strategy and set point. For fixed dry bulb control, we modeled several different set points. For this climate, the 70-degree set point resulted in the most energy savings. For fixed enthalpy control, the 28 BTUs per pound set point was the best. Now, if you remember from Eric's discussion of Standard 90.1, these are the same as what's required for Climate Zone 5A, which is where Columbus is located. Finally, differential enthalpy resulted in the most energy savings, but not all that much better than the other strategies. The second study was for a rooftop VAV system serving an office building. In this case, the economizer reduced HVAC energy use by 8 to 12%. Again, the best set points for fixed dry bulb control and fixed enthalpy control were still 70 degrees and 28 BTUs per pound, which is consistent again with 90.1. For this particular example, differential enthalpy control resulted in the most energy savings. However, the other control types were pretty good too. Interestingly, in this climate, enthalpy-based control did not provide a significant increase in energy savings, so fixed drivable control might be a more economical choice. While whole building energy simulation is certainly the gold standard for predicting energy savings from using an economizer, sometimes it helps to look at it in a different way. For example, we're used to equipment efficiency metrics like EER, provided at standard rating conditions. But it can be enlightening to use these same metrics to look at efficiency at different operating conditions. As an example, here's a 10-ton package rooftop unit operating at design cooling conditions when it's 95 degrees outside. So the outdoor air damper is at minimum position. The total power used by the compressors, condenser fans, and the supply fan is 9.5 kW. At this design capacity of 112 MBH, this equates to an EER of 11.8. But let's look at this same unit when it operates in economizing mode. Here it's 55 degrees outside, so the economizer opens the outdoor air damper wide open and turns off the compressor. So no power is used by the compressors or the condenser fans. Now for simplicity, I assumed constant speed fan, so the supply fan power is unchanged. But now the relief fan is turned on to maintain building pressure, so the total power drops to 1.5 kW. Now assuming the space temperature of 75 degrees, the cooling capacity of providing this 3,500 CFM of 55 degree air is 76 MBH. And the EER of this system is over 50. Really? Well, when Economizer uses only 1.5 kW to provide 76 MBH of cooling, that's pretty efficient. Now I assume the space sensible load was unchanged between these two conditions, as it might be for an interior zone. But if the space did not require as much cooling, the capacity provided by the Economizer would be less and this EER would be lower. However, if this was a variable speed fan, this fan power would also go down, which would cause the EER to be higher again. Now as another point of comparison, I changed the left-hand column to show the unit operating at the same outdoor condition of 55 degrees, but with the economizer disabled. So the outdoor damper is at minimum position, and this 55 degree outdoor air mixes with 75 degree return air. In this case, a compressor is operating to cool this mixed air to the desired 55 degrees. Without the economizer, the total unit power is 4.5 kW to provide the same 76 MBH of cooling at these conditions. And the EER is 16.9. Now this is higher than when the unit was operating at design conditions, but still much lower than when the unit is economizing. The main point is that the efficiency metrics we use to rate equipment don't include economizer mode. So this can be a helpful exercise to demonstrate its value.
Throughout the industry, most practitioners and organizations agree that economizers can be used to reduce HVAC energy usage. The requirements for economizer usage in 90.1 come from energy studies commissioned by the ASHRAE 90.1 committee. These studies have supported the usage of economizers in all but the most humid climate zones. Similar studies conducted by the Department of Energy, state energy offices, and university researchers also show significant energy savings potential. And all of the advanced energy design guides, which were published by ASHRAE and based on energy simulations performed by the Department of Energy, suggest economizers be used to reduce energy consumption in most building types. These and more resources are listed in your bibliography.
While the industry generally agrees that economizers save energy, sometimes they don't achieve the expected savings. There are a number of issues that can impede the operation of an airside economizer. So next, we're going to spend some time talking about some of these issues and ways to mitigate.
The first problem we'll discuss today is that in some cases the economizer dampers, actuators, and controls are not set up properly to begin with. This one's frustrating since the building owner is expecting everything to work, right? Unfortunately, steps sometimes get overlooked. For some projects, an on-site inspection by the design engineer can sometimes catch major oversights, particularly when coordinated with the installing contractor. A better approach is functional testing. This is oftentimes one of the tasks performed by a commissioning agent. But for some projects, commissioning might be too costly or too time-consuming. So even if the project does not include full commissioning, you could still require some degree of functional testing. This is where you might consider using some tools developed for California State Energy Code. That code has required acceptance testing of airside economizers for several years. Here's the form used in that state, which lists the steps for verifying that the economizer has been set up and is working properly. So if you're a design engineer or a facility owner, you could write into the spec that this type of acceptance testing is required for airside economizers. You might even require that test to be coordinated with a job site visit by the engineer. Now, to give you an idea how easy this can be, Eric and I used a package rooftop unit that's installed in our product display area to step through this acceptance testing process. On this 3-ton unit, some of the side panels are made of plexiglass, so you can see the components inside. On the left-hand side is the intake hood, which covers the outdoor air damper. Now, the first step of the acceptance test is to enable the economizer and simulated cooling demand. So we use the controller to change the high limit shutoff set point. I changed it to 140 degrees, which forced the economizer to be enabled, since the outdoor temperature is always below this limit. Then we watched as the unit responded. The outdoor damper moved to 100% wide open, while the return damper fully closed. This confirmed that the unit was indeed economizing and trying to provide all the cooling with outdoor air. Now, due to the demand for cooling, eventually the unit needed to start a compressor also. After the compressor turned on, we looked to make sure that the outdoor air damper remained wide open. This confirmed that it's operating in the integrated economizer mode. So the unit passed the first test. The second step of the test is to disable the economizer while there's still a cooling demand. So using the controller, I lowered the economizer set point down to 50 degrees, so it would be disabled. Then we watched as the unit responded. The compressor continued running, but the outdoor damper closed to its minimum ventilation position, while the return air damper opened. So it passed the second test. The third test is to switch the unit to heating mode and confirm that the outdoor damper remains at its minimum position. It did, so the unit passed this test too. For the final test, we turned the unit off and watched to ensure the outdoor damper moved to fully closed. So the unit passed all 4 of the acceptance tests. Now, hopefully this gave you an idea of how simple this type of acceptance test can be. The steps are pretty quick, but of course the controls of the unit are designed to not react too quickly. So from start to finish, this took us probably 20 to 30 minutes. But if you had multiple units on the roof, you could really do them all concurrently, which gives each unit time to respond to each test. That is, you would move from unit to unit to change the control settings, and then start back at the beginning to confirm that each one had the proper response. Another common problem is that the damper or actuator mechanisms can become worn or broken over time. This can result in a failure to achieve the expected cooling energy savings, or even an increase in energy use if the dampers are stuck open. Periodic inspection and maintenance can fix these problems, but that can be a challenge for some building operators who don't have the time, staff, or expertise to perform recommended preventative maintenance. Fix on fail really seems to be the norm for many organizations, but a failed economizer can sometimes be hard to notice, so it can remain broken for some time. This is not news to the industry. For years, the concept of automatic fault detection has been discussed and studied. The basic idea is that the HVAC controls could perform some simple checks and tests and then notify the operator when something doesn't seem right. For example, consider if the outdoor damper is stuck or if the actuator linkage is broken. The result is that the damper would fail to open for economizer when commanded to do so by the controller. This is referred to as a fault since the unit is not economizing, even though the current conditions suggest that it should be. As Eric mentioned earlier, new requirements for automatic fault detection for economizers have even been added to the latest version of the International Energy Conservation Code.
That's right. Part of the Economizer requirements in the 2015 IECC include fault detection and diagnostics. These requirements state temperature sensors must be permanently installed to monitor system operation. These sensors, located to record outer air, supply air, and return air temperatures, need to have an accuracy of plus or minus 2 degrees over the range of 40 to 80 degrees Fahrenheit, the same as 90.1. The unit controller needs to be capable of indicating different operating modes, including free cooling available, economizer enabled, compressor enabled, heating enabled, and mixed air low limit cycle active. In addition to this, the unit controller must be capable of showing the current numerical value of each aforementioned sensor. The unit controller needs to be capable of manually setting each operating mode to independently test the operation of the compressors, fans, heating system, and economizer. The fault detection system should be capable of detecting a number of standardized failures and faults. Examples include improper economizer operation, like when the economizer should be running and is not, or vice versa, and dampers that don't modulate properly. If any faults are detected, the controller must be capable of reporting them to a system that is accessible by operating and service personnel, or the faults must be displayed on zone sensors. John, have these requirements been implemented by manufacturers?
Yes, products are out there doing this today. Since January 2014, California's state energy code has required automatic fault detection for economizers on every air-cooled DX system that's 4.5 tons or larger. Here's a list of all the companies who have certified their fault detection systems with the state. So today it's pretty easy to spec this type of functionality. I suggest using the text from the IECC or the California code as the basis for your spec. Now to demonstrate, we went to a different package rooftop unit that's installed in our lab to simulate a fault. Since we didn't want to actually break something, we wedged the air filter in to block the return air damper from fully closing, which I suppose could happen if this filter was not properly installed in the filter rack. Then we forced the unit into the economizer mode and watched as the link, outdoor, and return air dampers began to move. When this return air damper closed down and hit up against this filter, it couldn't move any further. Then the actuator feedback mechanism indicated that while the economizer was enabled and being commanded to fully open, it was not able to open any further than about 20%. The unit controller recognized this as a fault, and this fault diagnostic message was then displayed for the operator. These diagnostics and alarms could also be communicated up to the building automation system, which could be used to send out notifications via email or text. And finally, some facilities subscribe to remote monitoring services, where these faults can be identified, even dispatching technicians to repair the problem before the facility manager even knows there's a problem.
Next, while sensors that measure dry bulb temperature tend to be stable and remain accurate for years, humidity sensors have often been notorious for requiring frequent calibration. For this reason, an economizer control strategy that relies on the measurement of humidity must consider the possible inaccuracy and ongoing maintenance requirements. Some engineers have proposed that any additional energy savings from enthalpy-based control might not justify the ongoing calibration requirement. Obviously, this depends on a number of sensors being used. For example, if a building uses a single centralized air handling unit, the added cost to provide a high-quality humidity sensor to enable enthalpy-based control and the need to periodically calibrate that single sensor may be worth the potential for increased energy savings in a humid climate. But if that building uses many smaller rooftop units, the impact on installed cost and maintenance is greater if each unit is equipped with its own dedicated humidity sensor. John, what does this look like?
As an example, consider a large retail store that's served by several package rooftop units, each equipped with an economizer. Now in a humid climate, an enthalpy-based high-limit shutoff strategy might provide the most energy savings. To implement this strategy, one approach might be to equip each unit with its own temperature and humidity sensors. But when you consider the added cost of the humidity sensors, the risk of inaccuracy, and the cost for periodic calibration, some clients might just elect to use simple fixed dry bulb control instead. But there are other options. If a building automation system is used, a single set of high-quality sensors might be installed to determine when to enable economizing. A decision that is then communicated by the BAS to all the rooftop units. Each unit still makes its own decisions about cooling or heating, but will only enable its economizer if the BAS tells you that the outdoor conditions are suitable to do so. Usually the individual units are still equipped with outdoor temperature sensors. So in the event that communication is lost from the BAS, this allows each unit to still operate its economizer in a standalone mode until communication is restored. Now, some projects install 2 humidity sensors for this purpose, and then compare the 2 readings as a check for accuracy. If the difference between these 2 readings exceeds the expected accuracy threshold, a diagnostic message is sent to the operator, and the system can revert to temperature-based control until the humidity sensors are recalibrated. Another approach is to have the BAS periodically compare the humidity sensor reading to a local weather data from the internet. Again, as a check to determine if the sensor needs to be calibrated. So while for some projects you may elect to go to simple fixed dry bulb control, others might justify the use of enthalpy-based control.
Some people are hesitant to use an Airside Economizer because they're concerned about it introducing more humid out air into the building. So choosing the right control scheme for the system and location makes a difference. If the building is located in a climate with high humidity, consider using a control strategy based upon outer air enthalpy, like the fixed or differential enthalpy controls with fixed dry bulb that John demonstrated earlier. These controls compute either the outer air or return air enthalpy condition and use that to determine if the economizer should be enabled. Implementing this control type may cost more up front, but it should yield better indoor humidity control. Also, it's important to select a system that uses integrated economizer controls. As John described earlier in the broadcast, integrated controls allow systems to provide 100% outer air to meet some of the cooling load, with the mechanical cooling meeting the balance of the load. The operating cooling coil should reduce the supply air dew point temperature to help keep the space humidity in check. John, you evaluated the impact of indoor humidity in your trace analysis, right?
Yes, in addition to energy use, trace can also simulate the indoor humidity levels in the spaces. If you recall, the first study was for a constant volume rooftop unit serving a retail store in Columbus, Ohio. Now in this chart, the y-axis shows the total number of hours in the entire year where the relative in the store exceeds 58%. The first column is our baseline, again the system with no Airside Economizer. For this example, there are 206 hours with elevated space humidity. As we've discussed in previous broadcasts, the basic constant volume system really matches sensible capacity to sensible load. Dehumidification capacity is really coincidental. As the sensible load in the space decreases, the constant volume system must deliver warmer air to avoid overcooling the space. The result is less dehumidification and higher space humidity levels. Now these remaining columns then show the impact on space humidity of using Economizer with various high-limit shutoff strategies and set points. As you might expect for fixed dry bulb control, with the higher set points, the number of hours with elevated humidity starts to increase. But with fixed enthalpy control, there's essentially no impact on space humidity, except for this highest set point, which did allow the introduction of a little bit more humid outdoor air. And finally, we see that differential enthalpy control can result in a few more hours of elevated space humidity in a constant volume system. Let's take a look at why this happens. The 28 BTU per pound set point that's typically used for fixed enthalpy control corresponds to 50% relative humidity at a 75-degree dry bulb. However, remember that in this basic constant volume system, the space humidity level actually rises at part load. So the return air enthalpy also rises. At this example outdoor condition over here, if the fixed enthalpy control is used, the economizer is still disabled. But if differential enthalpy control is used, the fact that the return air is more humid causes the economizer to be enabled sooner than it would with a fixed set point. To a point, this might result in more cooling energy savings, but it also results in bringing in more humid outdoor air, which can raise space humidity levels, as we saw in the previous chart. Let's move on to the second study, which was for a rooftop VAV system serving an office building, also in Columbus. The first interesting thing we see is that for the baseline system with no economizing, space relative humidity exceeds 58% for only 29 hours over the entire year, much less than in the constant volume system. Again, as we've covered in previous broadcasts, VAV systems generally do a pretty good job of limiting space humidity because they continue to deliver cool, dry air at part load conditions. That's certainly displayed in these results. The next interesting thing is that in this example, adding an economizer can actually reduce the number of hours with elevated humidity. I'll cover that more in a little bit. But similar to previous example, as the high limit shutoff set point is increased, the number of hours with elevated humidity also increases. This is also the case for fixed enthalpy control, although none of the set points resulted in more hours than the baseline system with no economizer. And finally, with differential enthalpy control, the number of hours with elevated humidity is still very low. So how can the economizer actually lower space humidity in a VAV system? Consider this example where it's about 47 degrees outside. Without an economizer, return air mixes with this outdoor air, and the cooling coil then cools this mixed air to the desired supplier temperature of 55 degrees. However, if the system is equipped with an economizer, the outdoor temperature is below the high limit shutoff set point, so the economizer is enabled. The outdoor and return air dampers modulate to bring in more outdoor air so that the mixture is equal to the desired supplier temperature of 55. When the dry bulb temperature is colder than 55, that air is also likely to be drier than the space. So the economizer brings in more of this dry outdoor air, and as you can see, this drier supplier results in a lower space humidity level. So these two examples support what Eric just said, that by choosing the right control strategy and shutoff set point, an airside economizer can be used to reduce cooling energy use with little or no impact on indoor humidity levels.
The next problem is specific to systems that use water coils in cold climates. If sub-freezing air moves through a water coil, the water inside the tubes can freeze and cause damage. Typically, a low-limit freeze stat is installed on the upstream face of the coil. And if the temperature of the air entering any section of that coil approaches 32 degrees, the controller responds by stopping the fan, closing the outdoor air damper, or both.
This affects an airside economizer because in some systems, the economizer might still be modulating to use this sub-freezing air for cooling. In this example, it's 25 degrees outside. The economizer is mixing 2,000 CFM of this outdoor air with 4,000 CFM return air. The resulting mixed air temperature is 55 degrees. But the problem is that this mixed air does not mix perfectly. This image shows a CFD model of what happens when this very cold outdoor air enters the mixing box. The air stratifies, with the warmer air near the top and the colder air down here near the bottom. Now the freeze stat is spread across the face of the coil. So if the air is cold enough down here, the freeze stat might trip, often shutting down the unit to prevent freezing. If this happens enough times, a frustrated operator will often disable economizer operation. Now the more savvy operator might just disable economizer whenever it's below freezing outside, but others just simply disable economizing altogether, thwarting the opportunity to save cooling energy. Now one approach to avoiding this is to include an air mixing baffles to improve the blending of this sub-freezing outdoor air with return air. This image shows the effect of this blender, minimizing this temperature stratification downstream before it enters the water coils. This reduces the risk of freezing and avoids nuisance freeze stat trips, so the system can achieve all the economizer energy savings expected.
The final problem we're going to explore is building pressure control. This becomes an issue when economizer operation overpressurizes a building. Some operators will decide to address this by disabling the economizer or disconnecting the actuator and dampers. But it doesn't have to be like this. A properly designed relief system can maintain building pressure even when the economizer operates. As we saw earlier, the outer air damper is wide open, bringing fresh air into the building. Somehow, that air needs to exit the building. In overpressurized buildings, exterior doors are difficult to close, and when they are open, they may become noisy with air rushing around them. As the pressure within the spaces and return air path increases, less out air can be drawn in for free cooling. In fact, Standard 90.1 requires a means to relieve excess outer air during economizer operation to prevent overpressurizing the building. The standard doesn't specify any particular system type, but there are options available to designers, including passive and active approaches. In our 2002 ENL on building pressurization, we discussed and demonstrated a number of options for building pressure control. I'm going to summarize some of those strategies here. One passive type is the use of non-motorized, gravity-operated relief dampers. Oftentimes, these are called barometric relief dampers and are typically used in small buildings and systems with ceiling return plenums. They're relatively inexpensive to install, but may need to be installed on multiple building faces to minimize wind effect, and each damper increases the number of openings in the envelope. Because they do not use controls or pressure sensors, they cannot maintain a set point. In some cases, the dampers can be placed in or near the occupied space, or in the return air plenum, as shown here. In this case, when pressure in the space increases due to economizer operation, the excess air exfiltrates through the envelope and the relief damper. This positive pressure pushes air through the damper and prevents the space from becoming overpressurized. Centralized barometric relief dampers may be placed in an air handler or package rooftop. Unit-mounted relief dampers are best located before the return air damper so they can open if the pressure in the return duct is high enough. This allows the return air plenum to be at a positive pressure while the unit's mixing box remains at a negative pressure. Like the local dampers, no controls or sensors are required. Spaces that relieve through centralized dampers tend to have higher positive pressures because the combined pressure drop of return grills, return ducts, and the return plenum must be overcome before the damper begins to open. There are active methods to control building pressure as well. One method is to use a relief fan in the exhaust air stream. This can be found in air handlers and package units. The central relief fan can be controlled in several different ways. One is to simply turn the fan on when the outer air damper opens to a predetermined position. Sometimes this is called central exhaust or powered exhaust. When the outer air damper opens to the predetermined position, the relief fan is turned on and the relief damper opens. The damper closes when the relief fan is off. The fan capacity is not modulated beyond on or off. Since the fan has a constant capacity and the amount of outer air varies during economizer operation, the pressure in the space can fluctuate. A relief fan can be modulated and controlled though. Sometimes this is called direct pressurization control. This is common with a VEV system or if demand-controlled ventilation is used. With the addition of a variable speed drive, a pressure sensor, and controls, a relief fan can directly respond to pressure changes caused by the system and building, which results in more stable, occupied space pressure. This type of control is more flexible than simple on-off control because the fan can be placed anywhere along the return air path and the set point can be adjusted. The relief fan is off if the measured difference between the outdoor and indoor pressure is acceptable. If this difference rises above a high limit, the controller modulates the relief fan to maintain building pressure within a specific range. If the return air path has a high pressure drop that cannot be overcome by the supply fan, a central relief fan may not make sense. Designers might choose to use a return fan, which works in series with a supply fan to share the workload. Like the relief fan option, there are different methods to control a return fan. For VEV systems, the central return fan will need some sort of capacity control. because the supply airflow changes, the return fan must also adapt to maintain building pressure control. There are several ways this can be done. Building pressure can be indirectly maintained by measuring airflow being supplied to the spaces, and a controller can subtract the expected local exhaust and exfiltration amounts from the supply airflow. This difference is the amount of air that needs to be moved by the return fan. Being indirectly controlled means it cannot compensate for changes such as local exhaust fan operation, wind, or stack effect. Another option is to add 2 pressure sensors to directly control building pressure. Here, a controller modulates a relief damper to maintain building pressure in a desired range. The return fan is modulated to maintain the static pressure set point in the return air plenum downstream of the fan. A centralized return fan with capacity control can provide stable occupied space pressure because it has the ability to compensate for other influences like local exhaust fans. And the operating set point can be adjusted. The use of a central return fan may allow the designer to reduce the size of the supply fan motor because the return fan is designed to overcome the return air pressure drop. But this is a more complicated system, and additional controls are required. Finally, the location of the return fan matters, and it must be placed in a way that it can draw air from all spaces. So for smaller buildings, barometric relief dampers may be acceptable. They may be local in the space or return air plenum, or they might be centralized and installed in the rooftop or air handler. But a central relief fan is preferred. On-off control is typically acceptable with a constant volume system. For a VEV system, or if demand-controlled ventilation is used, modulating the relief fan will provide better space pressure control. If the pressure drop in the return air path is too large, a return fan might be required. In this case, modulate the relief damper based upon building pressure and modulate the return fan to maintain return air plenum pressure. ASHRAE has published a guideline that helps designers set up, size, and control components used with Airside Economizers. ASHRAE's Guideline 16 discusses the 3 system arrangements we just covered and provides suggestions on how to set up and control relief dampers, relief fan systems, and return fan systems. They also provided suggestions on how to select and size dampers.
In most applications, an Airside Economizer reduces energy use. Of course, the amount of energy saved depends on climate, operating hours, load profile of the building, and proper functioning of the economizer itself. But there are some situations where implementing an Airside Economizer may not be feasible, even if codes and standards require it. Eric?
Right now, economizing is a prescriptive requirement in most codes and standards. But if an Airside Economizer is not feasible, the designer might consider using a water economizer instead. Or the designer might use an alternate path of compliance if the prescriptive requirements cannot be met. The energy cost budget of Standard 90.1 would require an energy model to show the building, as designed without an economizer, uses less energy cost than a compliant building that meets the minimum requirements and includes an economizer. Some systems, like air-cooled VRF, just aren't conducive to economizing, so exceptions might need to be used to exempt the system from the requirement. One exception in Standard 90.1 allows the designer to specify equipment with a higher part load efficiency value. The amount of improvement is a function of climate zone where the system is installed. Here you can see the table from the standard. If the piece of equipment has both full and part load minimum efficiency requirements, the part load value must be increased by the percentage shown here. For example, consider a unit installed in Yorktown, Virginia, climate zone 4A. To exempt this system from using an economizer, the part load energy rate must be increased by 42%.
While an Airside Economizer reduces energy use in most cases, there are some applications where the cooling energy saving benefit of the economizer competes with other components of the system. The first example is heat recovery. When a water chiller is used to provide cooling, the heat rejected by its condenser can be recovered to serve a useful purpose in the building. In some cases, this heat is used for preheating service water for restrooms, laundry, showers, or other processes. In other cases, it's used as reheat for humidity control or zone temperature control. So how does this affect the economizer? As we've discussed, when the Airside Economizer is enabled, there's less cooling load being passed on to the chiller. Since the chiller is doing less work, there's less useful heat that can be recovered. So while you're reducing the energy used by the chillers for cooling, the heating energy used by the boiler or electric resistance is increased. Now, some design engineers try to make the decision of which is more valuable, the economizer or heat recovery, and then implement just one of these strategies. If the heating loads are always greater than the heat available for recovery, then it probably makes sense to forget economizing and just run the chillers to recover as much useful heat as possible. Earlier, Eric mentioned several exceptions to the ASHRAE 90.1 requirement for an economizer. One of those exceptions addresses this conflict. But often the heating loads are smaller during the cooling season, and the chiller rejects more heat than needs to be recovered. In this case, you might consider limiting the function of the Airside Economizer so that it reduces the cooling load just enough so that the heat rejected by the operating chiller exactly meets the current heating load. This is sometimes referred to as a load-shedding economizer strategy. Now, another example of when the cooling benefit of an economizer competes with something else is when a humidifier is being used. When outdoor air is colder, it's not able to hold as much water vapor, so it's also drier. If the system requires humidification for a process such as printing, artifact storage, or certain medical procedures, bringing in more outdoor air for economizer can increase the need for humidification. To demonstrate, consider this 10,000 CFM air handler serving a museum. For this example, the indoor humidity must be maintained above 40% RH. This psych chart depicts the system operating on a cold day when it's 30 degrees outside. You can see that this air is also very dry. The Airside Economizer is enabled, so the outdoor and returner dampers modulate, bringing in more of this dry outdoor air to achieve the required supply air temperature of 55 degrees. But this supply air is too dry, so the humidifier is activated to raise the humidity level just enough to maintain 40% RH in the space. So while the cooling coil is able to be shut off, the humidifier adds about 45 pounds of water per hour, which equates to about 48 MBH. Now let's see what would happen if the economizer was disabled instead. The outdoor damper is closed down to its minimum position, so the mixed air temperature is warmer. Now the cooling coil must be activated to cool this air to the required supply air temperature of 55 degrees. And the resulting load in the coil is about 108 MBH. But with less dry outdoor air entering the system, the supply air is not as dry. In fact, at this condition, the humidifier does not need to operate to maintain space humidity. Of course, this is just one snapshot in time to explain this trade-off. For many applications that require elevated indoor humidity during cold weather, a water-side economizer would likely be a better choice since it will not have any adverse effect on humidification loads. And again, ASHRAE 90.1 does have an exception to the economizer requirement for certain areas of healthcare facilities and other spaces where humidification is required for process needs.
So energy codes are requiring economizers in more climates and ever smaller systems. But there are several considerations for maximizing the energy savings from an economizer, including the economizer control method, sensor accuracy, and ensuring building pressure control. The choice of economizer control might depend on climate zone and space humidity concerns.
For buildings with multiple systems, you might want to consider installing 2 centralized high-quality humidity sensors and use the building automation system to compare the readings against one another for accuracy, and then make the decision to enable the economizer centrally for all the systems in the building.
Selection and implementation of the relief system should be done right away. For VAV systems, use a relief fan unless the return air path necessitates a return fan system.
It's wise to commission the economizer once it's been installed. This ensures that the dampers, actuators, and controls all operate properly.
Don't forget to commission the relief fan system.
Consider using a fault detection and diagnostics system to continuously monitor the system. This can provide neat early warning for problems. You might even consider including Economizer fault detection in your spec.
And for systems where water coils might freeze during Economizer operation, consider using an air mixing baffle to avoid freeze-stat trips.
As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic, including the Engineers Newsletter Eric mentioned. For those of you seeking continuing education credit, be sure to check out our continuing education programs, which includes many past E&Ls, all free and on demand. And remember to fill out a survey and let us know what you think of today's program. AIA members, please turn in your information to your local site coordinator. And finally, please ask your local host about details for the remaining Engineers Newsletter Live programs. There's another E&L on easy methods to model chiller plants, which is available now. Then we'll return in fall to discuss new fan efficiency regulations and technologies, and acoustics and outdoor applications. So please plan to join us. Thanks for your time today. We look forward to seeing you later in the year.